So this is a brief of what we did. We talked about the first type of fixed partitioning management system. And anybody can give me a quick statement? Any description of the fixed partitioning? Do you remember? Can you tell me anything about the fixed partitioning system? All right, here we go. Volunteer, go on.
It gives out the fixed blocks of the memory and always the fixed amount of memory to the operating system.
Thank you. So when the computer is switched on and the operating system is uploaded, the memory manager will allocate certain area for the operating system. The rest of the area is all divided into variable size partitions of different sizes, and a table is created to hold information about each one of those partitions. How big it is, the address of this partition, and the status. That means, is it busy or occupied or free? And if it's occupied, what's the program ID or process ID that's really using it? So you need all that information. Now every time, so each partition, we know where it starts, at what location in memory, and how big it is. Each one of them, we know where it starts and the size of that partition. They're all written in the table. And whether it's free or busy. So that's the first thing. And then every time a program comes in, or a process to be uploaded or a program to be uploaded, we check how big is it, the size, and we go look for a partition that's free that can accommodate that program. And we always give exactly the same size or bigger. Most of the time it's going to be bigger. So let's say this is 500K, this is 400, this is 300, and those are 200 and 100 blocks. And this guy comes in and says, I need 425K, the size of this program. So it doesn't fit into those small ones, it only fits in the 500K. And it fits in this area, and the rest of the space is wasted space given to every program, and that's called internal fragmentation. So if you're asked, how does internal fragmentation happen? Easy. You say, we give a process or a program more memory than it needs. If we give you more than you need, any extra addition is a wasted memory, and it's known as internal fragmentation. So that's the fixed partitioning. It was not very efficient at using memory. And memory is very expensive, and it needs to be used very efficiently, as much as possible. So they developed, or they improved it into something called the dynamic partitioning system, which, if you are asked to describe it, you describe it as follows. You say, when the computer is switched on, the operating system is loaded into one part of memory and now the memory manager will keep the rest of all the memory in one big block and try to keep it in big blocks as much as it can. And it keeps two tables. One is the busy blocks, and one is the free blocks. And at the moment, there's no busy block, there's nothing in that table, and there's only one big block, only one. And how big is it? Could be the entire size of memory, whatever it is, maybe 8 megabytes, 8 million bytes, and it's free because it's in the free table. And we need to know, where does it start at? Again, the address, so it starts at this location, what's the end of the operating system, and now this is the user's kind of memory, starts at that. So that address and how big it is. So that's how it starts. Now every time a program comes in, this program comes in, It says I need 187 kilobyte of memory. So we go in and we look for a block. There's only one big block. Great, give it exactly 187K. This is program number 1, or process number 1. Now it's in memory. Another program comes in, and we, of course, we mark it here. We say this block now, it doesn't start at that. Let's say this starts at location 500. This no longer starts at 500. Now it starts at 687 because 187 is gone now. So we adjust this and say this starts at 687. We still have one block, and whatever size it is, it's less than that. And also in the busy block, we say, oh, we have a busy block that starts at location 500, and it's of size 187. And program number 1 is using it. So we have two tables, one of the free blocks and one of the busy blocks. And so on. So another program comes in, we put it here, so program number 2 is of 205K. We give it exactly 205K. This program comes in, says I need 413 kilobyte or byte. And this one, it says I need 12, or no, there's no such thing as 12, maybe 112 kilobyte, and so on. So many different programs come in, and they are given exactly as much memory. It looks very efficient. There's no waste at all up to this point. So this is one advantage of the dynamic. The dynamic, it has no internal fragmentation. That's very important. This one has a lot of internal fragmentation, but it has no external fragmentation. There's no wasted memory. If we give a program, we'll lose a bit, each program. But the rest of the blocks are available. Any free block is available, it's usable. So this one has suffered from internal fragmentation. Yes. Does it have external fragmentation? No. This one has no internal fragmentation. Let's see, does it have any external fragmentation? Yes, it does. Because, for example, if we have lots of programs that are busy, so this is busy, 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 and so on, so this table is going to be full, and this one still only has a small bit at the end, one free block, but it's going to be much smaller than it used to be. But let's say one program finishes. Let's say this program, 413, is finished. It's no longer busy, it's free. So this is gone. But we know it's 413. Now another program comes in, says, can I get 403 bytes? 403. So we say, oh, okay, if it's 413, this program number 7 comes in. We put it here, but it only needs 403, so it leaves 10K free. So we have a block here of 10K, it's free, and this one is only 400. We had a block of 413, and we gave this program 403 out of that. So that left us with 10K of free, while this one has become busy now. This is busy. So that's how external fragmentation happens. That's space that's left too small to be used, and it's allocated to no one. So we call it external fragmentation. And we end up getting a lot of these. Every time this program finishes, let's say program 5 is finished, this became free. This was 200K. That's fine. So now we have that free block and this free block. There will be 2 free blocks here. Maybe a few more. So if a new program comes in and says, I need 190 or 195, it will fit this one. So we take 195 out of this free block and we say now 195 busy. What's left is small tiny bit of 5 kilobyte of free space. And that's another fragmentation. And as the system keeps working, programs finishes, programs finish and more programs come in, we start giving them some of the free blocks, and that starts creating what's known as external fragmentation. So this one has no internal fragmentation, but yes, it suffers from external fragmentation. But the way it's designed to get rid of those fragmentation. So when a program finishes, see in this fixed partition you have one simple table. It has as many records as there are blocks, maybe 200 blocks, maybe 2,000 blocks, and each one of them is marked here. Is it free or is it busy? Is it free? Is it free? It's busy, and so on. And we know how big each one of them, a size and location, address. That's the table. And if it's busy, which program is using it? But anytime a program finishes, if this program finishes, and all we have to do is just mark it as being free. So we go to the place of the table where it says busy and just turn it into free. It's just like a hotel room, number 17, a customer leaves, it's free. We just go to the piece of paper on the table and mark it as being free. We don't have to do anything else. So this one is really easy to operate. Very little to do when you allocate. You search through the list and allocate, just make it busy and write the name of the program in it. While this one, now if it's busy, then we take it from this table, this block, and move it into this table by entry. And let's say this block is free, there's nobody in it, and this block is free. This is busy, these are free. So this is a block free of 205K. This one is a busy, 403, and there's a free fragment of 10K. Now if this program finishes, we move it to the free table, and we look, is the one before it in memory, is it free? Yes. Well then we'll join them. We'll make them a bigger block. So we have two free blocks. This is no longer busy, it's free. So we have a free before it, 205, and it is free. And the one after it is also free. So join them all into one block. So every time there are neighbors who are both free, we merge them together into one block. So instead of having 3 blocks, one of size 205, 403, and 10, we'll have one big block that has 205 plus 403, which is 608, plus 10, 618. So those 3 blocks, they become one block of 618 kilobytes, and it's free. And that's what we do each time a program finishes. And this is called the deallocation. So the deallocation, we look, any program that finishes and the block becomes free, we look at the partition before it. Is it free? Join them, merge them together, and the one after it. If the 3 of them are free, merge them. If only 2 of them are free, the one above it or the one below it, we merge them. And if none of them is free, leave it. You cannot merge. So this is part of the deallocation. Remember, when you allocate, simple. You go and look for a big block, cut the exact amount, allocate the program, and move that block to the busy table. Just so you'd have, well, it's like in a hotel, they say, okay, all the rooms that are busy we keep on one side, and all that are full or free, leave them to another side. We have 2 tables, 2 pieces of paper that we can check. So if somebody says I want to leave in a hotel, we look in the busy table, we find the room they're in, we say we mark it free and move it to the other side. So that's the dynamic partitioning, and it works, but it's still, sometimes we have a lot of fragmentations and they're not merged together. How do we know? Because sometimes we can find out the total size of all the busy blocks. For example, this one has a total memory of 8 million bytes, 8 megabytes. And we have, for example, busy, all the busy ones, 6 megabytes busy. So all the programs that are there, they occupy 6 million bytes. That means we should have 2 million bytes free. Sometimes you get a program that wants 1 million bytes and you cannot run it. Why not? Because, yeah, even though we have 2 million bytes, but they're all in small fragments. None of them is big enough to accommodate our program. Then you know, if you get many programs, if you know you have 1 million bytes free, and you get a program that's only 500,000 to run, and you say, I can't run you, yet you know you have 1 million bytes free, but you cannot run a 500 million program. That means that free memory of yours is too small. It's broken into small pieces, into small fragments. So that's one time when they know, oh, we have too many fragments. But you can't get rid of them until another program finishes, and you can merge it with the one beside it. Right. So they introduced the next one. Kamush. So the next one is called relocatable dynamic. So it's an improvement of the dynamic, and the way it works is quite similar. When you start first, the operating system is allocated whatever it needs memory, and we mark that part. We notice what address does it finish at, and that will be the starting address of one big free block. It's exactly how the dynamic works. And then every time a program comes in, we allocate it memory. So program number 1, 2, program 3, so they're all busy. Each program gets exactly as much memory as it needs. And then initially everything is beautiful and efficient. It's when they start finishing. When one program finishes and becomes free, and then another program comes. Let's say this one is 350, a program comes and say, I need 345. We say, oh, okay, here's a 350, we can do that, we can give you some of this. In fact, we give you most of it, and we are left. So 345 program is given here, and this is busy now, but this block is still free, and it's only 5K. Okay, so that's how we get external fragmentation. So if you are asked, how do you get external fragmentation? Maybe the easiest way to say, okay, to allocate a program from a block or partition that's only a little bit bigger than that program. So whatever is left is considered external fragmentation. They call it external because it doesn't belong to any program. No program is given that piece of, that 5 kilobyte is free. It's not given to any program, but it's too small to be used. And that's what a fragment is. That's what we mean by fragmentation. External fragmentation is a small amount of memory. It's free, but no program is not usable. It's not big enough to accommodate or be useful for any program. So now the problem is that we have loads of these. Eventually, as the program, more programs finish and more programs run in, so we start getting bits and pieces of external fragmentation, and they can get too much to the point that there's a lot of free memory available, but it's in small chunks that it's useless. That's up to this point, that's how dynamic partitioning system works. Now, what they decided to do, they have a program, they have a function called compaction. And compaction, everything stops working, and we start moving all the programs, the busy blocks, to one side, one end of memory, and all the free blocks to one end, and because they're all now next to one another, they're all free at the other end. So maybe we push each program upward, and the free memory goes down a little bit each time, and we keep moving that. So that's program number 3, program number whatever it is, 8 is moved up. Okay. So what's an external fragmentation? Okay. Yeah. What's external fragmentation? Okay, what's external fragmentation? And is it allocated to one program? No. So it's a small fragment of memory, a small piece of memory that's not allocated to any program, and it's too small to be useful for its own. So, in this example, in the compaction or in the relocatable dynamic, they say relocate the programs, push all the programs upward, so the gaps between them is removed. It's just like if we say, okay, can we push all the tables on up to that end of the room with no gaps between them, we'll have more space. That's exactly what happens here. Push all the programs upward and you end up having all the programs maybe coming to that point, and all these are internal, external fragmentations are all free to an end. So we push the busy blocks to an end and the free blocks to another end. And we merge all these free blocks. So we end up having one big free block of all the fragmentations. This is called compaction. The function is called compaction. When is it used? It's used in this system that's called relocatable dynamic partitioning system. That's the improvement they made to dynamic partitioning system to become the relocatable. Why do they call it relocatable? Because programs are changed, relocated, they're put in different locations. They're all pushed to one side, together, adjacent to one another, and all the fragments become together. And remember, we can, even in the older system, if there are two fragments that are next to one another, we merge them. So here we get all the fragments to one end. So instead of having 100 or 1,000 of small fragments, with tiny fragments, now we have one big block that we can run more programs. Of course, when you do the compaction, you stop executing all programs. And it's kind of a slowish operation, reasonably slow. It might take a minute or so, depending on the number of programs that are there. And the other thing, there's also another little problem when you move a program from its place. Let's say we have the CPU here. Normally when you run the CPU has a few small amounts of memory. They call them registers. Registers. The registers are small but very fast parts of memory. They're better, even faster than RAM. They're really extremely fast, but they're small. And this is where, for example, if you have a program number 3, for example, you have a program here, and you have it in memory, and you have the code for it located there, we always need to know where is the address of the first line of code for a program when it's put in memory. And operating system, memory manager keeps that. It's okay, this is in this block, and this is the first line of code at the start of the block address. Now, when it's time to execute, we don't run all the instructions. The CPU runs only one instruction. And the way it works, say, get me the instruction. So we know where the address is, so we send this to what they call instruction register. So there is one register in the CPU that says, get me the instruction to execute. And all the CPU does, boom, it's executed. Get me the next one, boom. So it keeps doing it so fast. It takes it 1/1,000,000th of a second to execute a program. So get me the next one. So the next one is, the CPU actually updates. When we're going to run this program, it says, where is the address of the first instruction? and we put it there. And the CPU puts that address there. So this is called the address register. So, for example, we tell the CPU this program is at 10,400,000. That's where it is. That's the first line of that program is at that address. It says, okay, the CPU tells the operator, tells memory manager, or tells the system, brings me the line of code that's at this address. And it goes to bring it, right? And while it's bringing it, it's going to bring it in less than a millionth of a second. While it brings it, it updates what's the next line of code. Let's say every line of code, I don't know, for this CPU, for example, 6 bytes or 8 bytes. Every line of code, maybe 8 bytes or 10. Let's just make it easy, 10 bytes. So it updates this one. The next line adds to it the size of the line, you know, each line. So say the next address of code is going to be at 10,410, which is the next line. That's all. But while this being brought in, this is put here, the CPU executes it and get me the next one. The next one is already, the address is there. So the system, the memory manager goes to 4010 and sends the next line. While this line is being sent, the CPU will increment this and say the next instruction is going to be at 420. It keeps adding. Unless one of your instructions says, no, go back to this address, it will update it. But otherwise, every program is executed in sequence, every line. It's just like you're cooking a recipe, you have to follow it in sequence. Unless the recipe says, go back to step number 3 and do it again, or something like that. So sometimes in programs as well, you get a line that says, go back to this location. Then also the CPU will know. It will not be executing the next line, it will be executing that line that's mentioned, so it will update it. But that's what the CPU does each time. So get me the next line, boom. And while you're bringing the line, it updates what the next line is. So when it finishes here, so you get me the next line, already we have the next address, That's how it works. Now, imagine we stopped the execution and we call the compaction function. Now this program is moved. It's changed from, it used to be at 10,400, that's where the first line is. Now it's moved to whatever it is. Let's say we moved it here to 9,400. We moved it up 1,000 bytes in memory. We changed its location. Remember, the next time we're going to execute that, the memory manager is going to give the CPU the new location of this program. This program is moved here. That's what the compaction function did. So it's moved to line 9,400, not 10,400. So, but the CPU doesn't know that, and all it has to do to go to this line, you cannot change the location of your address halfway through. So what they did, they added another register, and they call it the compaction register. Is that what they call it? I think they call it compaction register. We'll see the right name. And the compaction register could be minus 1,000. Now, because the compaction actually, or the relocatable register, the change of position register. So we moved it from 10,000 to 9,000. We moved it up minus 1,000. So sometimes you actually end up moving a program downward and another program upward. So this could be in minus, it can be in plus. So if the memory manager, your compaction moves the program, it keeps an idea of where is the program now. We cannot change the original address, 10,400, but we'll change the value here from 0 to minus 1,000. So now, every time the CPU wants to calculate where is the address of the next line, it takes that address, the original address, plus the relocatable address. So it says, okay, I'm at line, the last line I executed was 10,420, but now it's going to be minus 1,000 because everything moved up 1,000 back. So it's going to be 9,420. So that next line is going to be somewhere here, which is exactly where we move this program. So this relocatable, or this compaction function, it works. It kind of gets all the three partitions together. But by moving those programs, it causes that little issue of a problem for the CPU to know when did you move this program. But because of this is the relocatable amount that you moved the program up or down, it's kept and it's put into another register. And even before moving, it's say the program is here. The original address, what's value here is 0. The CPU still, every time it wants to calculate the address, it says, where is the starting address? Add to it any changes. And the changes are 0, so it always adds this. But initially, 0, it changes nothing. For example, the program was at line, or at memory address 10,400 plus 0, it says it's 10,400. But if we move it down 2,000, then we have to change here plus 2,000. So always add that original starting address of the program or the line where we're executing plus the relocatable extra shifts that we have to do up or down. It can be in a plus or it can be in a minus. So that's another complication that was added because of the relocatable address. So this relocatable address, it has better advantage over dynamic because it can reclaim back this function. If you're asked what is the compaction function? What's its function? What's its purpose? It reclaims back all the small fragments of memory that are useless, that are too small. It puts them together, brings them back into the system, they can be reused. So it claims back or reclaiming the external fragmentation. But it has two problems. It's slow. It's very slow. So it actually, every time you want to run it, all programs have to stop working. And it takes a bit of time. So that's one disadvantage. The other disadvantage, as well as being slow, it creates this other complication of when a program is moved to another place, the CPU kind of gets a little bit, doesn't know where it is, and therefore they had to add another address, which is called the relocatable address, or the shifting, the amount of shift that was made as part of finding out the address of the next instruction to execute. So what's the instruction register used for? What do you expect to find in the instruction register? Anybody know? How many instructions? Okay, the instruction register. What is it? Any idea what does the instruction register contain? What information would it contain? Anybody? The actual address of the instruction? What about the address register? Remember, we have two. Now, at this stage, we have two registers. There are about 8 or 16 registers. Each one of them is there for one purpose. The instruction register holds the instruction to be executed. Anytime you have a line or you have a program of 10,000 lines, 10,000 instructions, anytime you want to execute one of them, we bring it from wherever it is in memory. Remember, the CPU doesn't go there to execute. You bring your instructions to the CPU. So each time we bring one instruction, one line of code. This for now, say one line of code. But what exactly to be more efficient or more precise, it's one instruction. You bring one instruction, put it in the instruction register, and the CPU will execute it. And then we bring the next one, and the CPU executes. So the instruction register holds the instruction to be executed. To be executed. And then we bring another one. And the address register holds the address of the next instruction. The CPU updates it and says, okay, when I execute this, don't forget to bring me the next one. And if you want to know where the next one is, there it is, it's in the address register. So the address register always holds the address of the next instruction to be executed. And the next instruction is brought in. And every time the instruction is brought in, the address is incremented. It's like you're sitting in a group and we're having a test, oral test. Okay, next student come in. So every time the next student, based on a student number. And I have the list of all the student numbers. I do one and then I add one to it, the next one. Add the next student. So we have an address and we have the actual instruction itself. So what's the advantage of the relocatable dynamic? How good is the relocatable dynamic? It doesn't have, say again? Yeah, it gets rid of fragmentation, but remember, it allows them to happen. And then until we execute the compaction function. The compaction function is a slow operation. You don't want it to always be running. You don't want to frequently run the compaction function. Because every time you run it, all programs stop working for a few seconds. And that's not good. So that's the advantage is that it will bring back all the fragments and claim them back and make them join them into one big block that we can then, after that, we run programs that we couldn't run before. But remember, the disadvantage is that it's too slow. So it's not something that you want to run frequently. So when is the good time to run? Anytime, anybody knows? Can you think of when do you say, okay, you're responsible for the system and all the programs are running? When is a good time to run the compaction? Will we run it every hour? Will we run it every month? Maybe it's not frequently. When is a good time to run? Any ideas? When do you think we should run the compaction operation? Remember, it's slow. You don't want to run it, any time. You say, okay, let's run it every 5 minutes. During a period of low activity. What's the main purpose? What's the purpose of the compaction function? So if we have lots of fragmentations, we can claim them back. And that happens if we have lots of activities, we have lots of programs running. If we don't have many programs running, then there's no problem with fragmentation. So it's not really when things are low, when the activity is low. When the activity, for example, we can run maybe 50 programs, but now we're only running 5. If we're only running 5, there's no fragmentation problems. Most of the fragments have already